The journey of our waste begins the moment we throw something away. It all starts with our household trash can, where we dispose of unwanted items. We then empty our indoor trash into a larger outdoor bin for collection. The average American generates about 4.9 pounds of trash daily. This adds up to approximately 292 million tons of municipal solid waste annually in the United States. What many don't realize is that throwing away is just the beginning of a complex journey for our waste. From your trash can, waste embarks on a multi-stage journey through our waste management system. As we move forward, we'll explore each step of this journey, from collection to processing and beyond. Now that we've seen where the journey begins, let's follow our waste to the next step. On collection day, specialized garbage trucks with hydraulic compactors arrive to efficiently collect household waste. Modern garbage trucks feature powerful hydraulic compactors that compress trash to approximately 1/4 of its original volume. This compression allows trucks to collect significantly more waste before reaching capacity. Municipalities typically schedule different collection days for various types of waste. Regular household trash might be collected twice weekly, while recycling and yard waste have their own designated collection days. Garbage collectors handle an impressive workload. A single collection route typically serves between 800 and 1,000 homes per day, collecting as much as 12 tons of waste in a single shift. The waste collection process is a critical link in the waste management chain. Garbage trucks move systematically through neighborhoods, collecting waste efficiently before transporting it to transfer stations for further processing. With their specialized equipment and efficient routing, collection trucks form the backbone of our waste management system, moving waste from our homes to the next stage of the process. Transfer stations serve as crucial intermediate facilities in the waste management process. After collection, garbage trucks bring waste to these transfer stations before it reaches its final destination. At transfer stations, initial sorting takes place. Workers and machinery separate recyclables and hazardous materials that shouldn't proceed to landfills. A key function of transfer stations is consolidation. Waste from smaller collection vehicles is transferred to larger long-haul trucks or trains, making transport more efficient. This initial sorting and consolidation at transfer stations is essential for efficient waste management, reducing transportation costs and keeping harmful materials out of landfills. Landfills are the final destination for approximately 50% of all municipal solid waste in the United States. Modern landfills are carefully engineered structures, not simply dumps. They feature multiple protective layers, including clay and plastic liners, to prevent contaminants from leaking into groundwater. When trash arrives at a landfill, it's compacted into layers to maximize space and reduce air pockets. Each day's waste is covered with a layer of soil to minimize odors, control pests, and prevent trash from blowing away. Once a section of the landfill reaches capacity, it's sealed with a final cover of soil and vegetation. Contrary to popular belief, landfills are not designed to break down waste, but rather to store it while minimizing environmental impact. The dry, sealed environment actually slows decomposition significantly. Modern landfills include sophisticated systems to collect leachate, the liquid that forms as waste breaks down, and to capture methane gas that's produced by decomposition. This methane can often be used as an energy source. We now enter the materials recovery facility, where recyclables are sorted and processed. In the United States, approximately 32% of waste is recycled or composted, diverting valuable materials from landfills. When recyclables enter the facility, they travel along a complex system of conveyor belts, where various sorting mechanisms separate different materials. Powerful magnets pull out ferrous metals like steel cans and tin. Optical sorters use infrared light and cameras to identify different types of plastic. Eddy current separators use electrical currents to repel non-ferrous metals like aluminum. Human workers also play a critical role, manually removing items that automated systems miss. Each type of material follows its own path through the facility. Once sorted, materials are compressed into dense bales that can weigh up to 1,500 pounds. These bales are then shipped to manufacturers who transform them into new products, completing the recycling loop. The efficiency of recycling facilities depends greatly on how well we sort our recyclables at home. Contamination with non-recyclable items can disrupt the entire process. Waste-to-energy plants represent an important alternative to landfills, handling approximately 12% of all waste in the United States. In these facilities, trash is burned at extremely high temperatures, between 1800 and 2000 degrees Fahrenheit. This intense heat converts water to steam, which drives turbines connected to generators, producing electricity. Modern waste-to-energy facilities use advanced filtration systems to significantly reduce harmful emissions. These include scrubbers, electrostatic precipitators, and selective catalytic reduction systems. The energy potential of waste is significant. 1 ton of municipal solid waste can generate between 550 and 750 kilowatt hours of electricity. This is enough electricity to power an average American home for approximately 3 weeks, demonstrating how waste can become a valuable resource for energy production. Composting is nature's way of recycling organic materials and turning waste into a valuable resource. When organic waste ends up in landfills, it decomposes without oxygen, producing methane, a greenhouse gas 25 times more potent than carbon dioxide. In the United States alone, about 25 million tons of food waste is sent to landfills each year. This generates greenhouse gas emissions equivalent to 3 million cars. Composting this waste could reduce methane emissions by up to 50%. There are 2 main approaches to composting: large industrial-scale operations that process tons of organic waste, and smaller backyard systems that individuals can manage. Industrial composting facilities process tons of organic waste daily. They maintain optimal conditions with temperatures between 130 and 160 degrees Fahrenheit. The entire process typically takes 3 to 6 months to produce finished compost. Backyard composting is accessible to anyone with outdoor space. It works best with a mix of green materials, like food scraps, and brown materials like leaves and cardboard. The process may take anywhere from 3 to 12 months, depending on your climate and management. The composting process relies on microorganisms like bacteria, fungi, and various invertebrates. These decomposers break down complex organic materials into simpler compounds, eventually creating nutrient-rich compost that can be used to improve soil health. Compost offers multiple benefits. It improves soil structure and fertility, reduces the need for chemical fertilizers, helps soil retain moisture, diverts waste from landfills, and significantly reduces greenhouse gas emissions. Composting completes the natural cycle of growth, consumption, and decomposition. By composting our organic waste, we're participating in nature's recycling system and helping to build a more sustainable future. The problem of plastic, where does it really go? Despite recycling symbols on plastic products, the reality of plastic recycling is disappointing. Only about 9% of all plastic is actually recycled. A staggering 8 million metric tons of plastic waste enters our oceans annually, causing devastating effects on marine ecosystems. In the environment, plastic doesn't biodegrade. Instead, it breaks down into smaller and smaller pieces called microplastics, which can be ingested by marine life and enter the food chain. One challenge with recycling is that different types of plastic require different recycling processes. While PET and HDPE types 1 and 2 are commonly recycled, most other types are rarely processed. Much of what we call recycling is actually downcycling. While true recycling turns a product back into the same type of product, downcycling converts plastic into lower quality products that cannot be recycled again. So where does our plastic actually go? About 12% enters recycling systems, but only 9% becomes new plastic products. 3% is downcycled. The vast majority, 79%, ends up in landfills, while 9% makes its way to our oceans. Understanding the true journey of plastic waste is the first step toward developing better solutions and reducing our plastic footprint. E-waste includes electronic devices, mobile phones, batteries, and household chemicals that require special handling. E-waste contains hazardous materials that can harm human health and the environment. Let's look at some of these toxic components. E-waste requires special handling processes to safely manage the hazardous materials. E-waste recycling facilities can recover valuable metals from electronics. Circuit boards contain gold, silver, copper, and palladium. Recycling e-waste is more efficient than traditional mining. 1 ton of circuit boards contains up to 800 times more gold than 1 ton of ore. While e-waste represents only 2% of mass in landfills, it accounts for approximately 70% of the toxic waste. Globally, over 57 million tons of e-waste was produced in 2021, but only 17.4% was properly recycled. Improper disposal of e-waste leads to serious environmental problems. Toxic chemicals can leach into soil and contaminate groundwater. These toxins can cause soil contamination, water pollution, and affect plants and animals through bioaccumulation. Proper e-waste disposal starts at home with separate collection, then is sent to certified recyclers for disassembly and material recovery. This proper recycling flow ensures that valuable materials are recovered and toxic substances are safely handled, reducing environmental impact. As we look toward the future of waste management, a key goal emerges, moving toward zero waste. Our current approach to waste follows a linear model. We extract resources, produce products, consume them, and dispose of waste. In contrast, a circular economy aims to eliminate waste by keeping materials in use through better design, reuse, recycling, and recovery. This model significantly reduces waste by creating a continuous flow of materials through the economy. New technologies are revolutionizing waste management. AI-powered sorting systems can identify recyclables with greater accuracy than ever before. Chemical recycling breaks down plastics into their base molecules, allowing them to be reused for new products, instead of ending up in landfills. Robotic waste management systems can sort materials continuously with high precision, significantly improving recycling rates. Several cities around the world are leading the way toward zero waste. San Francisco diverts over 80% of waste from landfills through comprehensive recycling and composting programs. Ljubljana in Slovenia and the town of Kamakatsu in Japan have implemented innovative policies that dramatically reduce waste. Vancouver and Adelaide are also making significant progress. These cities succeed through strong policies, public education, well-designed collection systems, and extended producer responsibility programs. Each of us has a role to play in moving toward zero waste. Reducing consumption of single-use items is one of the most effective actions. Composting food and yard waste keeps organic materials out of landfills where they produce methane, a potent greenhouse gas. Learning the proper recycling guidelines for your area ensures materials actually get recycled rather than contaminating the recycling stream. Choosing products with minimal packaging and supporting businesses with sustainable practices creates market demand for better solutions. Moving toward zero waste requires systematic changes and individual actions working together. The circular economy model represents a fundamental shift in how we think about materials and waste. Every action we take to reduce waste contributes to a more sustainable future. The transition to zero waste isn't just possible, it's already beginning in cities around the world.